welcome to this interesting video where we would be discussing how to convert a decimal number to a binary number and then display it on a 7-segment 4-digit display. The primary components that we would be covering in this video are first, Simulink model, which would essentially contain the logics for conversion of decimal number to binary number. There would also be a provision to manually increment the decimal numbers by 1 each time the user presses a push button. That a particular logic would also be there in Simulink. And finally, the display logic for the 4-digit 7-segment display that we would also be implementing using Simulink. We will use an Arduino board to flash these models, and that would essentially be serving as a microcontroller to control the display and the push button. So that being said, we would be using a 4-digit 7-segment display and an external push button trigger for manually incrementing the decimal values. So before moving on to the actual model, let's dive into how this 7-segment display actually works. The hardware that we would be using is 5461AS1 for our purpose. As we can see on the right, each digit will have 7 segments and 1 decimal point over here. These segments are marked as A, B, C, D, E, F and G. Whichever segment is activated, that particular segment will be lit up. That means that if we want to display 3, we would be activating A, B, G, C and D, as we can see here. If these segments are activated, then the digit 3 would be displayed. So in total we have 7 pins for each of these 7 segments, 1 for the decimal point, which makes it 8. Then we have 4 extra pins for each of these digits, D1, D2, D3 and D4. Now how the 7-segment display works is, if we activate a particular segment or a particular number of segments, then that particular segment in all of the digits are activated at once. So let's suppose we activated for 3 A, B, C, D and G, then these particular segments will be activated for all the 4 displays, all the 4 digits, D1, D2, D3 and D4. Now if we want to display 3 on the 2nd digit, then we just activate D2 at that time and then the corresponding pins for these particular segments, and then we get 3 on the 2nd digit. Similarly, if we want to display any number on D4, then we activate those particular segments for that number and then also give a high input to this D4 so that this particular digit is activated. Now the question arises, if we want to activate different numbers in different digits, for example if we want to display 1, 2, 3, 4 in these 4 displays, then how can we do that? The answer is, we use the theory of persistence of vision, which means that if a particular image changes at a rate faster than 1/16 of a second, then our mind sees it as continuous. What we would be doing is, we would be sequentially switching between these digits in a very fast manner. So for example, if we want to display 1 here, we would be activating segments B and C and D1, so that the segments B and C is activated for all the displays, but since only D1 is activated, 1 would be displayed on the 1st digit. At the next instant of time, we would be activating 2, so the segments corresponding to 2 would be A, B, G, E and D, and then we would be activating D2 at the same time. So although the segments for 2 will be activated in all the digits, since only D2 is activated, so 2 will be displayed here. Similarly, 3 would be activated for D3 at a time when D3 is given as high, and similarly 4 at D2. Now this switching from D1 to D2 to D3 and to D4 and back to D1, this should essentially be done in a time less than 1/16 of a second, so that we see that all the digits are continuously being displayed as 1, 2, 3, 4 instead of sequentially moving from one to another. So that is the main concept on which this 7-segment 4-digit display will be working. So now we know the working of this, let's dive into how the model is constructed and its working. have the model ready. Let us see step by step what all components are used here and how the model is constructed. The primary blocks that we have used are the Arduino digital in and digital out pins, which are available in the support package for Arduino, which can be downloaded as a plugin or add-on in Simulink. Other blocks are just the basic Simulink library blocks, which are available by default. Here primarily three things are happening. First of all, there is an initial value from where the count will begin. Then there is this digital input from Arduino board. I'm using pin 13 as the assigned digital input to the model, that is the output of the Arduino. And here we will actually be connecting a push button switch, as I'll show in the hardware connection. Once we press the switch, this is actually an active low pin, that is why it gives 1 by default when it is not pressed. Once it is triggered, this will give 0, which is inverted here, and then this goes to the SR flip-flop. The basic functionality is that once the push button is pressed, it will set this for just one sample time, because we have added a delay here. So in the next sample time, this set was 1, and then reset also goes as 1. So it will then toggle it and make this output as 0. This is to ensure that for however long you press the push button, this captures a single pulse at a time. Otherwise, what may happen is if you press it for, let's say, 0.5 second also, and let's say the sampling time of this model is 0.1 second, then it will capture 5 pulses during those times, and then the counter value would increase by 5. So we don't want that to happen, and that is why we have connected an SR flip-flop to take care of that situation. It will take one press as one pulse, and that will go over here, add 1 to this counter value, and then give the output. This is just for adding cumulative values, because we want to remember what was the last counter value. Let's say you have already increased the count to 1, the next time you press it, it should increase to 2. So this 1 would already be there in the output, which will be fetched by this memory block, and then it will be added to the fresh value coming from the SR flip-flop as 1, so that the counter will again increment by 1. This is how the external trigger from the push button will function. Next, we have the decimal to binary conversion here, because the input coming from the sum block is a decimal number, but we want our 7-segment display to have a binary output, and that is why we are converting the decimal to binary here. We can see this is a normal conversion logic that we use for decimal to binary. We do the mod operation by 2, whatever is the remainder goes as the output bit, and then we divide it by 2 and again perform the same operation. Since here we are designing a 4-bit binary display, so we have 4 such mod and division operations here. The first bit, that is the bit obtained from the first mod operation, will be the least significant bit, that is why it is mentioned as LSB here, D4, and then subsequently the D1 will be the most significant bit, or MSB. This is given to a bus, and this binary out is going as a bus signal. This is the decimal to binary conversion. After it has been converted to binary, then comes our main logic of displaying it in the 7-segment display. As already told in the presentation, we are using a 4-digit 7-segment display. There the logic is that it uses mux-ed signals. It will display 1 digit at a time, and we have to use the theory of persistence of vision to make it look like all the 4 digits are displayed at once. However, it will not be the case. For doing that, we have used a counter over here. This counter is a 3-bit counter. Since it is a 3-bit counter, its value will go from 0 to 3. It is a free running counter, which means that after 3 it will reset to 0 and then again start the count from there. What it is doing is essentially changing between these 4 bits sequentially and then repeating the same thing again. These are the digit activating pins, so I've used pin 9 through 12 for the 4 digits as input, D1, D2, D3, D4, and it should be noted that these are active low, that is, it needs a 0 input to get activated, and that is why we have used a not equal to comparison here. Other pins, which are for individual segments, that is pins 2 through 8, these are active high, which means that these need 1 as input to be activated. The logic is that when a particular segment is activated, you can visualize it as, let's suppose segment A is activated, so it will be activated for all the 4 digits at once, and whichever digit is selected through these 4 pins, the segment A for that particular pin will glow. Now we only have to display 0 or 1, right? So what we are doing here is we are selecting 1 digit at a time, and then moving to the other digit in the next clock pulse. So in this way, we are switching through all the digits one by one in a very fast manner, which gives the illusion that all the 4 digits are active at once. So when the counter is 0, this will go as 0 and others will go as 1. So D4, which signifies the least significant bit, will be activated when the counter is 0, and similarly when the counter is 3, then the digit corresponding to most significant bit, that is the one on the leftmost side, will be activated. So sequentially each of the digits will be activated, and then at the same time when this let's suppose D4 is activated, then we will be seeing whether it should display 0 or 1. When the counter is 0, then subsequently this D4 bit will be going as the output from this multi-port switch, and then let's suppose D4 is 1, then it will be inverted, and then these will go as 0, which means that segments A, D, E, F will be deactivated, and segments B and C, which are the rightmost edge of the digit, will be activated, and therefore 1 will be displayed. So you see here 1 is always given to segments B and C, and G is always set as 0, because we only have to display 2 digits in all the 4 digits that are 0 and 1. And if you look closely, segments B and C will always be activated whether it is displaying 0 or it is displaying 1, and similarly the segment G, which is the one in the middle, is always deactivated. Therefore these are permanently given as 0 and 1 respectively, irrespective of the digit which will be displayed. Now we saw that when D4 is 1, then A, D, E and F will be deactivated, only B and C will be activated, and therefore 1 will be displayed. Now when D4 is 0, then the display for D4 should show 0 essentially. So when D4 is 0 and when the counter is counting from 0 or set as 0, then this particular D4 pin 12 will be activated, so the display corresponding to D4 will be activated, and then this 0 is passed through this NOT gate, transformed to 1, and then going to segment A, D and F, A, D, E and F, which means that segments A, D, E and F will be 1, and these two are already 1. Therefore these segments A, B, C, D, E and F will all be activated, and therefore 0 will be displayed on the D4 display. Similarly, let's consider the next one, D3. When the counter is 1, D3 will be passed, and similarly when the counter is 1, this particular comparator will give 0 as output, and therefore this D3 will be activated since it is active low. When D3 is activated and this is passed, let's suppose this was displaying 0, similar to the one we discussed before, the 0 should be displayed on display D3, then this will be transformed to 1, and then again segments A through F would be activated, and therefore the digit which will be displayed will be 0. If it is 1, then it is inverted, and then segments A, D, E and F will be deactivated, only B and C will be activated, which means that the digit displayed on D3 will be 1, which is what we require, and same is the case with D2 and D1. So you see, each time a particular display is selected, at the same instant that particular display is activated, and then the same is passed forward and the segments corresponding to that particular digit is activated, so that either 0 or 1 is displayed on the respective digit, D1, D2, D3 or D4. So that is the overall logic for displaying this binary number. It is all because we want to reduce the pins on the display. This mux-ed logic helps us to reduce the number of pins on the hardware, thereby making the connection simple. That is all there is to this logic. Now let's see how it is actually implemented in the hardware and how it works. So as we see here, this is the wiring connection that we would be doing in the hardware. This is our Arduino Uno board, and this will be the 4-digit 7-segment display. This here is our push button, which we will be using to increment the value of the counter by 1 every time we push it. So we are using pin number 13 as an input trigger via this switch. Pins 9 through 12 are used to activate the 4 displays D1, D2, D3 and D4. Other pins 2 through 8 are used for individual segments of each displays A, B, C, D, E, F and G. One of the pins of the digital display is unoccupied here because this is for the decimal point, which we are not using currently. We are tapping the ground from the Arduino board itself as one of the terminal connection of the switch. We have the layout ready with us. Let's get to the actual hardware connection. Now before deploying the model on the board, there are few changes that we have to do in the model. Here a convert block
would be required because this would be giving a binary value. Although this would also do, it's a good practice to convert it to a decimal or integer value while summing, so that we have a decimal in here. Also, while building this decimal to binary logic, I forgot to mention that these division outputs should be integer values. Essentially, these should use a floor function and then give out a lower approximated integer value. To do that, the output data type should be set to unsigned int. This should be done for all the 3 gain values. Once this output is unsigned int, for a mod operation to happen, the second input to this mod should also be an unsigned int. So this constant value should also be set to unsigned int. And for this mod operation, since it is expecting the first input from this input value should also be set to unsigned int. We will set the simulation time to infinite. Then we go to model settings, where we will configure the solver. So I've kept it as fixed step and the solver is selected as OD4. Sampling time is kept as 1 millisecond. Then we go to hardware implementation and select Arduino Uno from here, since we would be using this board. If it is connected to your PC or laptop, once you select this Arduino Uno, it should detect this host board connection automatically. For me, it is selected as USB serial 1420. And once these are configured, we can click OK and start to deploy the model on board. To do that, we can go to Hardware tab, select Build, Deploy and Start. So we see it has started building the model. So it is being flashed on the board, and now the deployment is complete. Since we have assigned pin number 13 to this push button, so as soon as we press it, the decimal count should increase by 1, and so after converting it to binary, it should display it over here. So if we press it once, we can see the count increased by 1. 0001 in binary is equivalent to 1 in decimal. If we press it again, it should display 2, and here it is 0010 equivalent to 2 in decimal, then 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. This is the maximum value that a 4-digit binary display can show. If you press it again, it will go to 9, and then since 9 is represented by 1 and 4 zeros, so in these 4 digits again it will go to 0000 and again essentially start the entire sequence. So this is how we can build the logics in Simulink and then flash the code, generate the code out of it, and then flash it on our Arduino board after making the proper connections. So this is what I wanted to show in this video. Hope it was interesting, and thank you for watching.